Recording now. Take it away, Tom.
Well, good morning and welcome back to Tom Talks. If you've been with us before, it's been a few months. Can I get this white box to go away? I wonder.
It's probably just notifying you that we're recording.
Okay, yeah. Can you see the white box?
Yes, it's blocking the image.
Okay, all right. Well, anyway, if you haven't been with us before, I hope you enjoyed today. But whether you have or haven't been with us before, make sure if you have questions, either put them in the chat or wait for a pause and you can just unmute yourself and ask the question. To me, that enlivens the presentation. Having questions, that interaction makes it easier for me and easier for the people that are listening. So feel free to ask your questions as you have them.
Hey, Tom, that box is still there. You might have to click something on it.
I'm trying to click something on it, but there's no little X.
You have to acknowledge that we're recording the session.
Account owner can watch this recording if it's stored. Oh, I'm sorry. I had to click the got it button. Okay.
That's okay. Should be good to go now.
Okay. Well, history of climate and what to expect. But back when did we do this, Jackie? It was in the spring sometime. We early summer we met and we started talking about potential topics for Tom Talks at the end of the year. And this is one of them, climate. And I thought to myself, well, every single day I read the newspaper, we get a couple of them here, and every day there's at least one article about climate change on the front page. It involves climate change. It may not be directly about it, but if you read the articles, it's in there somewhere. It's on the TV news very frequently, if not every day, in every single newscast. It's there. In a week, you'd be almost certain to have several mentions of it. And anyone who wants to know about it can go on Google and put in climate change and get about 1,000 hits. And you could pick some of the reputable sources, and you could just keep learning and learning and learning about climate change in the past and present. So I thought to myself, well, why would I do a talk on that if it's sort of an old topic? It's current, but it's an old topic and it's in the news all the time. But then I thought about climate change and conservation, and as I'll describe later, climate change threatens to really change all the parameters of conservation. You might say to pull the rug out from under conservation as we know it today, at least the threat. So that's interesting. That to me is interesting and is an opportunity for us to think about why we do conservation. Once I had that idea, I thought, well, I need to talk to my friend Grog, which is kind of an unusual name, but you'll see why it's an unusual name here in just a second. Just to kind of talk through what conservation means in the era of climate change. What you're going to see next is just a recording of that conversation. Well, hi, Grog.
Good morning, Tom.
Hey, I was putting together a talk on climate change and...
You wanted to get my opinion, right?
Yes, you have a unique perspective.
Not so unique from where I'm sitting. We're all Neanderthals here, but go on.
With the threat of climate change, why should we conserve nature?
Isn't it obvious?
I don't mean just having enough wood to burn or animals to eat.
Wow, 50,000 years later, and you still haven't figured it out?
Well, yes, that's why I asked.
I guess Homo sapiens aren't all they're cracked up to be. Okay then, take this little gray moth.
Hey!
What good is it anyways?
Hey!
I can't eat it, or make clothes, or home out of it.
Obvious.
It's not as pretty as a butterfly, and if the climate warms, it's likely to disappear. Poof! It's gone. And then it would be replaced by other moths from further south. Is that good or bad? Is my moral judgment even relevant here? If everything changes in time, even people like me will disappear one day, leaving only a few bones behind with no record of our thoughts and cares. So is holding on to anything possible? If this little moth and others like it are going to disappear one day, and they are, regardless of what I do or don't do, what's the point of holding on? Is it just to make sure certain plants and animals are available for me to use? Let's think about this. I don't hold on to my children just to use them for something. I raise them to be who they are. I only try to optimize the things that I use, making them bigger and better over time, precisely because I don't care about them. Of course, I care about a tool, but I only care about its usefulness. Defining a relationship solely because of something's use to me is dangerous. It divides us from all that we use, leaving us alone in the world.
That sounds pretty bleak.
It is, but there's a better alternative. We can instead respect and reveal the nature of each place. We must find somewhere within its borders, its woods, its slopes and streams, and learn how it came to be what it is. That is hard, but not impossible. It's a relationship you live in and will never finish. It's true, the world would be a little bit uglier without this moth, and less familiar. I wonder if this moth and all the other creatures disappeared, would I still be me? What if I am all the things I have known and done, and all the places I've lived? What if everything that made me, me, disappeared? Would I still be the same person?
Here it comes.
Would my home be home without an echo of my childhood memories and parents' and grandparents' stories? I would be homeless, a nowhere man.
Or moth.
Maybe conservation only makes sense within the world I live in and the time I live in it. Maybe holding on is fundamentally human. Holding on to what must inevitably slip away is how we find permanence in an impermanent world. Simply using the world for its resources was never a whole relationship. It's too lonely. Maybe saving funny, familiar little fellows like this moth makes sense after all.
You got that right.
Thanks, Grog.
Not so bad for a Neanderthal after all.
It's about 25 degrees here today.
Down there, Tom. Yeah, Grog is a pretty deep guy. I can always count on him to get to the bottom of the issue. We're going to come back to that before we're finished today, because I think in many ways, even though it will take up a minor part of the presentation, I mean, it was the heart of the presentation and the reason why I chose to do it today. But for right now, let's move on and talk about climate change and how it happens, not just today, but historically.
It's about 25 degrees here today. The sky is perfectly clear. It got down probably in the low 20s last night. We expected to hit 40 degrees by the afternoon today, and probably mid-40s later this week and into next week. If you go back about 4 months to late July, it was 90 degrees in the afternoon, and if we go forward a couple of months into January, we expect the temperatures to be well below freezing, maybe sub-zero, maybe 40 degrees. We really don't know. I mean, what I'm talking about here pretty obviously is weather.
So what's the difference between weather and climate?
Well, weather is what we feel right now. So weather is that momentary condition of the atmosphere at one place at one time. So we could measure it in temperature, humidity, wind speed. Climate, on the other hand, is something quite different. If we look at changing patterns of weather over long periods of time, generalized across a whole region, those changing seasonal patterns of temperature, humidity, rainfall, etc., that model we call climate. So there's a difference between weather and climate. Weather is what you feel. Climate is this model we create for changing patterns of weather over time. So when I talk about climate today, or climate change, I'm really talking about changing weather patterns across the entire surface of the Earth over long periods of time. So it's a very big model of many, many different weather observations. So weather relates to climate in the same way that I as an individual relate to the species Homo sapiens, or a tablespoon of seawater relates to the ocean. The larger category tells us, just frames our expectations about what the small could be, but the small really doesn't tell us much at all about the extent, the range, the extremes of the larger. I mean, knowing that the temperature today at 9:30 in the morning doesn't tell me really anything about the climate, or very little, whereas knowing that we live in a humid continental climate really doesn't tell me much about the weather right now. So that's that difference between the experience of weather and that model of climate.
So that's really where I wanted to make that distinction to start with. I think it's so commonly becomes confused that we hear so much about climate change and we expect to be able to walk out of the door and feel it or sense it or see it in some way, but it's not something you can see. The reality of climate change, however, is pretty obvious to climate scientists and has been for many decades. It's just temperature anomalies over the last century plus, and you can see an obvious warming trend. And that warming trend is reported by oceanographers, it's reported by climate scientists, it's reported by people that are studying glaciers at the South Pole and ice sheets at the North Pole. It's reported everywhere. And melting permafrost is one of those important issues of climate change. We're not going to deal with it here in Illinois, but it's huge because as that permafrost melts along the coast here, it's breaking apart. But probably more important in terms of the world is that melting permafrost gives off huge amounts of carbon dioxide and methane when it starts to melt, which only exacerbates and increases global warming going forward. Sea level rise is, again, simply an historic observation. It's going up as ice caps and glaciers are melting. In the future, low-lying areas like Florida and along many of its coastlines would risk, it doesn't have to be completely covered in seawater to change the distribution of freshwater aquifers, to change rates and directions of coastline erosion. This is an important human issue. Here is California, where coastlines are disappearing. So there are problems in climate change that relate to nature. We're going to talk about more toward the end of the presentation, but there's a lot of them that just relate directly to human beings and our lifestyle and our infrastructures, where we live, how we live, all of those things. Rising ocean temperatures are changing life in the ocean, and as you raise the temperature of the ocean, the carbon dioxide that is in the ocean comes out of solution and goes back into the atmosphere. That's a very important, huge storehouse of carbon dioxide. When it's dissolved in the ocean, that will come out of the ocean into the atmosphere and further increase global warming, and can lead to things like coral bleaching. Coral reefs are some of those biologically diverse ecosystems on Earth, and they're fast being impacted by global warming. But let's look at some of the mechanisms. These are mechanisms of global change in climate, and they have importance over the whole history of the Earth. So this really isn't about climate change in the present. This is about how the Earth's climate has changed over literally billions of years, hundreds of millions of years. And just to give us some context for understanding climate change in the present. And the first thing I want to talk about is the astronomical hypothesis. That was a huge breakthrough in the early mid-20th century by a Serbian mathematician named Milutin Milankovic. and this is the age before calculators, much less computers, he realized by talking with astronomers that the Earth's orbit wasn't a completely stable entity, but rather shifted cyclically over time. And it shifted cyclically in three ways. There's the eccentricity of the Earth's orbit, so it's not completely circular around the sun, it's an ellipse, and the shape of that ellipse changes. The tilt of the Earth's axis changes relative to the plane of the Earth's orbit around the sun. And precession, which is an odd word, but it's actually something you're quite familiar with. So let's just take a quick look at that. This is changes in the eccentricity of the Earth's orbit, and you can see it becomes more eccentric and then less eccentric over time. And the cycles of those changes are about 100,000 years. And as it becomes more eccentric, excuse me, let me go back. Anyway, as the Earth is closer to the sun, we have hotter summers and warmer winters. As the Earth, as the orbit becomes more eccentric, then it can exaggerate or nullify some of the differences between summer and winter, because when we're further away, we're receiving less solar radiation. This is the tilt of the Earth's axis, and it's 23.5 degrees right now, but you can see it changes back and forth between about 22 degrees and 24.5. So we're kind of right about in the middle right now. And as the Earth tilts, you can see if the sun is on the right-hand side, the northern hemisphere would be in its summer right now. It would be getting the brunt of the sun, whereas the southern hemisphere will be getting the sun at a very low angle. Likewise, if the sun was on the left, which is kind of where we are right now, we're December, getting close to December 21st, the northern hemisphere, the sun is impacting the surface at a very low angle. The sun is low in the southern sky, and so the amount of solar insolation, the intensity of sunlight is lower. Therefore, the heat input in the northern hemisphere is lower. At this time, we would actually be in winter. At this time, if the sun were on the right side, we would be in a northern hemisphere summer. And that angle changes over time. So the difference between summer and winter changes over time. The precession is a fascinating thing. You all know about precession because you all played with tops when you were children. And if you spin a top, you notice how when you first spin it and it's going at a very high revolutions per minute speed, that axis of the top is pretty stable, but as it slows down, it starts to wobble. And that wobble is precession. And even when it doesn't seem to be wobbling very much, it is at a very tiny amount, still going through precession and a tiny bit of wobble. Now, the Earth is wobbling, and as it wobbles, it obviously changes the angle of the Earth's axis to the plane of rotation around the sun, but it also moves the sun. It also moves summer and winter to different stages, different stages in that eccentricity of the Earth's orbit. So all these things come together and they overlap one another, and you can create this diagram. Now, Milankovitch figured this out before computers, so he did this by hand, and he figured out for a number of times in the Earth's past the amount of solar insolation meaning the amount of radiant energy coming into the atmosphere. And you can see it going up and down over time, and those three different cycles overlapping. So it's not like a perfect sine curve. Rather, it's the overlapping of three sine curves that are at different frequencies. And so you get this up and down movement. And we can see here, like the end of the Pleistocene is this upward movement, this increase in solar insolation around 10, 12,000 years ago. There's the cooling of the Earth that puts us into the Wisconsin stage of the Ice Age. Let's go back here. And we can see here I'll just go to the next. So in the end here, you can see actually solar insolation has been falling recently, but this is the effect of the increase in greenhouse gases, that it's holding that temperature up and in fact increasing when it might be decreasing in response to a decrease in solar insolation in the present. Now let's look at another. So that's a mechanism that's changing the Earth's climate really on frequencies of thousands of years. Now let's look at some other mechanisms that have caused the Earth's climate to dramatically warm and cool off, generally on cycles that are or on timescales much longer than that. So, for instance, the asteroid impact at 65 million years ago that terminated what we call the age of dinosaurs, really the heyday of dinosaurs. The Mesozoic ended 65 million years ago. The life on Earth changed dramatically as a result of a huge asteroid impact. We now know that was roughly in the Gulf of Mexico where that asteroid struck. The initial impact of that is just to send a huge, massive dust cloud and basically cast a shadow over the whole Earth. And so there's an abrupt, rapid cooling, as much as 30 degrees Fahrenheit in the global temperatures over in the short term over a matter of centuries. But what that asteroid did when it hit the Earth was to vaporize a lot of the bedrock, which a lot of it is limestone, lots of carbon in limestone. And so as that vaporized, that carbon goes back into the atmosphere as carbon dioxide. So after that brief rapid cooling event, there is a longer period of elevated temperatures as a result of a huge asteroid impact. And we'll see that in some temperature graphs here in a minute. Look at some geological hypotheses. Volcanic activity, some things we've experienced in relatively modern time. Volcanoes inject millions of billions of tons of dust into the atmosphere, but even more importantly, they eject a lot of sulfur dioxide and carbon dioxide into the atmosphere. The carbon dioxide directly contributes to climate warming. The sulfur dioxide mixes with water, forms sulfuric acid, which then reacts and forms sulfur aerosols, which tend to reflect light, much like dust particles in the stratosphere. So that has a cooling effect. The carbon dioxide will have a longer term warming effect. Both of those things are important to changes in the Earth's climate. There have been periods in the Earth when there were major periods of volcanic activity, and those end up stimulating a great warming. And again, we'll see that in some graphs of Earth temperature changes over the last roughly billion years. And some of those warming periods were as a result of volcanic activity. This is just Mount Pinatubo in the Philippines in 1991. Actually caused a measurable global cooling of about 1.3 degrees Fahrenheit. I'm going to show you this picture of plate tectonics, the movement of climates, what was called in the early 20th century what is it? I can't think of the name. We'll forget it for now. So let's look at climate change, and this takes us back about 200 million years. And now we're going forward. You can see the North American plate here, South American, African, Eurasian here. This is Antarctica, what will become Antarctica. There's Australia there, and this is India, which doesn't look like it's in the right place now, but just watch it as we still come forward now about 80 million years ago. India is headed rapidly toward the Eurasian continent and will smash into the Eurasian continent and create the Himalayan mountains. Australia is drifting northward from the polar regions. So that was climate. That was the distribution of continents. So what on earth does that have to do with climate? Whoops. Let's go here. So if we go back in Earth history, the climate or the continents, or what we think of as continents today, sometimes they were the same continents, sometimes they were slightly modifications of those continents. They were in different positions on the Earth. The equator was always a warmer place. The poles were always colder places. So when we have large continental masses at high latitudes, meaning toward the poles, during cold phases of the Milankovitch cycles, we have the potential for an ice age. We have the overlapping of those two influences. If all the continents continental masses are clustered around the equator, even in cold phases of the Milankovitch cycles. You can't really produce an ice age. It's not cold enough to build glaciers at the equator.
Tom, we have a question.
Okay, go ahead.
Is there evidence that the meteor strike affected the Earth's wobble?
I don't know. It might have affected it in the short term, but I would think well, I'd have to look that one up. I don't know. You'd think if it affected anything, it might have. I mean, gyroscopes are amazingly stable things. And even an impact to make a crater that's, I've forgotten how wide, 100 miles wide or something like that in the Gulf of Mexico is still relatively small relative to the mass of the Earth and the spinning mass of the Earth, and it's got gyroscopic stability. So I would guess that was pretty small, but I don't know. I don't know if it was measurable or even speculatively from the present age.
Thanks, Tom.
Plate tectonics and ocean circulation. As those climates move, they change where the oceans are, where there are gaps between continents. And that's big because the ocean, water, has an incredible ability to hold heat. More than any rock substance, water has a huge ability to hold heat. And as water moves, ocean currents move around the Earth. They're transporting heat. And so as we change those ocean currents and the transport of heat, we change the distribution of heat on the Earth's surface, and it has a major impact on climate. One of the speculative problems with warming is that the ocean circulation pattern that gives rise to the Gulf Stream will collapse at some point, and that has a dramatic warming effect on Western Europe. If that happened, then Western European climates I mean, this is all speculative, of course, but over a period of decades could become much, much colder as a part of global warming. And this is carbon cycle, but this is carbon cycle on a much longer than what you think of as a carbon cycle you learned about in school. And we'll look at that carbon cycle here in a few minutes. But this is, let's just follow carbon of rain falling out of the sky, picking up carbon dioxide in the air, which forms carbonic acids. It falls on the continents and then dissolves limestones and other carbonate rocks on the Earth's surface. That dissolved calcium carbonate then flows into the oceans, where that is picked up by shelf-forming organisms, of which there are many in the ocean. Those shells accumulate at the bottom of the ocean and form limestone again. And that limestone becomes part of the Earth's crust. The Earth's crust is moving as a part of plate tectonics. That Earth crust is eventually subducted, moved below other continental plates. And as it does that, it's heated, melted, and that carbon is vaporized, and it comes off in volcanic really chains of volcanoes around the edges of subducting continental plates. And that carbon is injected into the atmosphere again. It then falls as rainfall. And so that's a cycle that takes hundreds of millions of years, but it's another very important carbon cycle because there's an awful lot of carbon tied up in the rock of the Earth, particularly in those sedimentary rocks at the surface of the Earth. Biological influences. So there's been life on Earth for like 3.5 billion years, and we'll see that life on Earth is all carbon-based. And as life on Earth changed over time, in particular photosynthetic life and its ability to take carbon out of the atmosphere and make it into biological material, as life evolved, there were major periods of where that carbon was sucked out of the atmosphere. And when you take carbon dioxide out of the atmosphere, it cools dramatically, just as when you put it into the atmosphere warms again. So simple carbon cycle. This is kind of, probably you saw this for most of us. We saw it in grade school, again in high school, and probably many times since. So we have plants that are taking carbon dioxide out of the atmosphere. That carbohydrates now are eaten by herbivores. The herbivores can be eaten by carnivores. those animals plus the plants are respiring, are burning up those carbohydrates for energy and releasing carbon dioxide. Eventually, the animal or the plant dies through decomposition. That carbon is released and goes back into the atmosphere as carbon dioxide. That's a pretty short-term cycle, a matter of, it could be months to years to centuries, but pretty short-term cycle of carbon coming out of the atmosphere into plants and then going back into the atmosphere again. If some of those plants and maybe a minor amount of animal life end up as fossil organic deposits that eventually mature into fossil fuels, that can be dug up and then sent back into the atmosphere as we burn up those fossil fuels. There's a cycle that takes hundreds of millions of years. Coal is roughly coal age, so you're talking about 300 million years. Oil, I think, is a bit older than that. So we're talking about a very long cycle. So whereas this short cycle more or less is carbon neutral. Carbon comes out of the atmosphere, goes right back in again a few years or a century later. Whereas this one, there could have been periods in the Earth, like in the Earth's history, where the carbon dioxide contents were much higher, global temperatures were much higher, plants were sucking that carbon dioxide out, eventually storing it as fossil fuel. It's now being released. So that threatens to change the whole pattern of Earth's climate over the last few 100,000 years. So there's the long-term storage, and that release is the problem we're dealing with today. The short-term storage, not so much of a problem. That's roughly, we can think of that as carbon neutral in terms of climates today and climate change today. So let's look at some of those biological changes. This is going back 2.5 billion years with really the invention of photosynthesis, which leads to a huge increase in oxygen contents in the atmosphere because it was largely carbon dioxide before that that's sucked out of the Earth's atmosphere. The oxygen is released. The carbon is tied up into organic chemicals, so that there's a big decrease in carbon dioxide content, which plunges the Earth into a super ice age. A little bit later, about 700 million years ago, you have the evolution of multicellular life, large organisms, both photosynthetic organisms and larger animals. Those sink to the bottom of the ocean and begin to accumulate. So again, you're pulling carbon dioxide out of the atmosphere, and again, that leads to another cold phase in the Earth's climate. Again, 400 million years later, you have the evolution of land plants. Before that, the surface of continents. Oh, I just remembered when I was talking about plate tectonics, it was continental drift. When you're in front of an audience, sometimes simple words are hard to think of. So the evolution of land plants before 400 million years ago, the continents were bare rock, bare eroding rock. After 400 million years ago, rapidly the Earth's continents are colonized by plants in increasing layers and layers of plants in the development of woody plants and forests. So you have a relatively long period when that buildup of organic carbon on the surface of the Earth is changing, and that's starting around 400 million years ago. That's around the time that our bedrock, or the Silurian bedrock in the Chicago area, was deposited. So now let's look at how climate has changed in Earth history. And you can see, just to jump over here all the way to the right, this is a reconstructed temperature graph. We'll talk just in a few minutes about how they would construct a graph like that. But here we are today, and you can see, yes, the Earth has been a whole lot warmer than it is today in the past. I mean, in the recent past, in the Quaternary, so going back, 3+ million years, no, the Earth has been relatively cool. And so when we talk about global warming, we're talking about it in the context of a Quaternary, life in the Quaternary, the life we have around us today, the whole distribution of ice sheets, ocean levels, all of these things that are in our history over the last few centuries. That's what we're talking. We're talking about that climate changing dramatically from where it is today. and causing huge problems, both in conservation and human infrastructure and life. So here is the evolution of cyanobacteria, and you can see that ice age back in the Precambrian. Here is multicellular life evolving right at the end of the Precambrian. Again, plummeting of carbon of temperature. The evolution of land plants sort of happens stage-wise from the Silurian into the Devonian Carboniferous development of forest, and we have a lot of Carboniferous fossils in our Pennsylvania rocks here in Illinois. I talked a little bit about that in the Geological Tom talk. I don't know, it was last year or the year before. So again, plunging the Earth into another ice age. Tectonics and volcanism are really the reason for these dramatic warming events after those cooling events. This is the asteroid impact to end the Cretaceous in the age of dinosaurs here, the Triassic, Jurassic, Cretaceous, or the Mesozoic, and what we call the age of dinosaurs. It ends, there's the abrupt cooling event, and then there's a warming event due to the increase in carbon dioxide content, and then a cooling after that. Earth's time over the last 65 million years, again, you see the relatively cool phase after the impact of the asteroid, and then a warming after that, and then a slow cooling through the tertiary into the modern period, and the dramatic cooling that sends us into the ice age. I mean, what I'm trying to do today is put the Earth's climate into context. We're sort of talking about the same as we were talking about the difference between weather and climate. Talking about climate change today is taking a very, very brief window of the sort of climates that have shaped the world around us today and human habitation of the Earth today. And we can see the Earth was drastically different if we go back very far, but we don't really want the Earth to be drastically different. We live in the Earth today, and its change away from what we consider normal today is the problem. It's the problem in conservation. It's the problem with climate change. How do we know about these temperature changes over such vast periods of time? Well, if we're only going back a matter of centuries, we can look at tree ring analysis and growth rates of trees. Sediment cores can take us back tens of thousands of years, so we can look at changes in vegetation. I mean, we can see the Chicago area changes from a boreal vegetation dominated by spruce trees 13,000 years ago to a climate dominated by broadleaf trees about 10,000 years ago, and that continuing more or less into the present. That's reflecting those different climatic phases. We can go back much further by looking at ice cores in Antarctica. We can go down, and it turns out that as snow falls out of the air and slowly is compacted and turned into ice, it traps little bits of air in it. And that air, we can do ice cores down into those sheets of ice that are up to 8,000 feet thick in Antarctica, and go back hundreds of thousands of years and look at carbon dioxide contents in the atmosphere that then obviously influence temperatures. Another indirect way of looking at temperatures is doing sediment cores. Whenever we find calcium carbonate material, limestone, whether it's fresh shells or whether it's rock, we can date the time that the original calcium carbonate was formed by looking at the oxygen that becomes a part of that CaCO3, the calcium carbonate, because we can look at the isotopes of oxygen that were incorporated into the calcium carbonate, and those isotopes of oxygen will tell us about the amount of ice on the Earth at the time. And so we can use the oxygen isotope method to go back as far back into the past as we can find limestone sediments. So those graphs are not a wish and a hope. They're actually looking at the Earth, looking at in ways that we can measure temperature indirectly going back hundreds of millions of years. And we can look at fossils in the same way we're looking at fossil pollen here. We can look at actual fossils of organisms and see the tropical floras and faunas changing to temperate and temperate floras and faunas. Okay, we're about halfway through. What we're gonna do next is to look at sort of modern theories of climate change, greenhouse effects, carbon sequestration, and then conservation in the age of climate change. But I want to pause now to see if there are any questions. What we've done so far is to really look at the broader history of how climates have changed on the Earth, and at least some answers to the question about why they've changed. And we've seen that carbon dioxide has been a major actor in those dramatic changes in climate, either by carbon dioxide being taken out of the atmosphere with the evolution of photosynthetic organisms and land plants, or in dramatic increases into carbon dioxide with things like asteroids hitting the Earth or periods of very active volcanism. So we're going to take it forward. Any questions right now, or we can go forward.
Just as a reminder, you can put questions in the chat, or you can unmute and ask your question. And either way is perfectly fine. Just fill in a little bit of time in case anybody is typing and
Okay,
wanted
well,
that. So
okay, well, let's look at carbon dioxide and its role in climate change. This is one that's I hear people talking about carbon dioxide.
did you get a question in the chat?
Go ahead.
Okay, so we have, it's my understanding that the ozone hole has very little to do with global warming, but will that ozone hole continue to enlarge as the centuries pass?
The ozone hole is a different phenomena. It is it happens with as a result of the production and release of chlorofluorocarbons, which is huge in the late 20th century. And those get into the atmosphere and they eat up ozone, which if they stayed in lower atmosphere, we might even think of them as good because ozone can be quite destructive. It's a pollutant that can form in the lower atmosphere as a part of smog in cities, and it destroys lung tissue. It can destroy plant tissue. It's pretty nasty stuff. But in the upper atmosphere, in the stratosphere, it actually screens out harmful ultraviolet light. Without an ozone forms in the upper atmosphere as ultraviolet light hits oxygen molecules and breaks them apart, and they reform as O3 or ozone. So that's kind of the story of natural ozone formation in the stratosphere. We were releasing chlorofluorocarbons. They were getting into the atmosphere, and they're great ozone eaters. And they were decreasing the amount of ozone in the upper atmosphere, in particular at the poles, because you have a circular pattern of wind at the poles through the Antarctic or Arctic winters. And so there's a prolonged period of time when there's no mixing, and that chlorofluorocarbons are just eating up the ozone. And then as that circumpolar wind breaks up in the Antarctic or Arctic spring, those ozone depleted atmosphere drifts northward over Australia or over northern Europe, and you get a lot of ozone depleted air, which means tremendous amounts of ultraviolet light coming to the surface that weren't before. So skin cancer. This is a digression, I realize that, but it's actually a good digression, one I had thought about doing anyway, because it's really about how people can react to global atmospheric phenomena in positive ways. With the threat of increasing skin cancer rates in Europe, North America, and Australia, there was dramatic change in reduction in our production and and release of chlorofluorocarbons. And since then, there's been evidence that the ozone hole is started to close. It was a product of our release of chlorofluorocarbons as we've taken those out of, as we stop releasing them, that problem has at least decreased. I'm not saying it's over. I haven't really, this is research I did some years ago on this topic. But my point would be that we actually did something. People actually did something. They saw a huge problem, a global level problem. They did something. They changed the chemistry of our air conditioning, which was one of the major uses of chlorofluorocarbons. And we did something about it. So there is the potential for global problems don't have to end in tragedy. They can actually end in creative solutions. So I'm kind of glad that question was asked. I apologize if that seems like a long digression. There may be some relationship to global warming. I'd have to do some more research on that one, but I don't think it's tremendously related to do, other than as you have more global warming, you'd have more people turning on air conditioners, which would, if we hadn't gotten rid of using chlorofluorocarbons as a refrigerant. So there was that indirect relation, but thanks for the question anyway.
Got a couple more questions in the
Okay.
chat. When
You just talk
carbon
long enough, people will ask questions.
when carbon enters the soil through root growth, does the soil exhale this carbon dioxide and methane as the roots die and decompose? Or does the carbon stay entrapped for a good amount of time, or at least a long time?
We're going to talk about that toward the end of the presentation today as a part of our discussion of carbon sequestration. The answer would be yes, carbon is stored in the soil. And in wet soils, methane can be stored in there also. And as temperatures warm, there is a threat that carbon could be vaporized again and methane released into the atmosphere. I talked about that. I mean, the storage of methane and carbon in soil is what I talked about very briefly at the beginning of the presentation when we were talking about thawing permafrost. Same phenomena in other places, just not quite as dramatically. But we'll talk more about carbon storage in soil before we're done today.
One more for you. Will human-induced climate warming factors trump any new ice age?
In the short term, probably yes. But in the long term, probably no. The long term, we're talking about thousands of years. What we're talking about, the threat of global warming, that threat is accumulating over decades and certainly, hopefully getting it under control within 100 years. Whereas the ice age and that is really more of a, if you would call it a threat of glaciers encroaching on Northern Europe and Chicago being covered in ice again. We're talking about many thousands of years. But it will happen. I mean, we're still in the end of the Pleistocene. There's every expectation that in the geologic future there will be glaciers also again in the Midwest.
Any last questions out here? If you want, you can unmute and ask.
Okay, well, let's start to look at carbon dioxide. It's a tiny part of the atmosphere, but a very important part of the atmosphere. And as we'll learn, the fact that it's both important and tiny is the problem. It could be important and big, and it wouldn't be a problem, or it could be small and not important. But the fact that it's important and very tiny is the problem. I'll give you time to read this. I just got this out of just a couple weeks ago. It's what I say. It's always in the newspaper. Signs we're making progress against global warming. Sounds ambitious or not. I'm not as much of a pessimist as Luann. I know it is very easy to be a pessimist looking at global warming. We are not doing nearly enough to reduce release of or the burning of fossil fuels. But there are also things, the conversation, I know it's just conversation, but the conversation has shifted dramatically since 1970 when I graduated from high school and there was the first Earth Day that summer. The conversation has shifted dramatically since then. And climate change is now a scientific fact. The model of climate change and its relationship to carbon dioxide is a scientific fact today in the sense that things can be scientific facts. There are electric cars today. I mean, that was a pipe dream when I was in high school. I remember looking at pictures of them. I'm very mechanically oriented sort of a guy, and I would read Popular Mechanics, and they'd show pictures of cars, and they probably weighed 20,000 pounds because they were all these lead acid batteries, and they could go 30 miles an hour, and you'd have to recharge them every 30 miles, and they didn't seem very practical. But now, not only do we have electric cars on the road, every single automobile manufacturer in the world is coming out and doing huge amounts of research and development of electric vehicles. We have programs of carbon sequestration now. We'll talk more about that at the end of the presentation for sequestering carbon both with trees and in soil. There's a lot of movement. We have renewable energy. I mean, drive across Illinois and look at the wind farms, solar farms. I can walk down the street and see solar panels on houses. I realize that's not enough, but it's hugely different than it was 3 or 4 decades ago. This shows change, and to me, it's hope. And that's, once you lose that, you've lost everything.
A lot of people think climate change just doesn't make common sense. You know, I get that. I mean, people are little creatures, and the Earth and its atmosphere are so huge and vast. I mean, how could one possibly affect the other? But referring to common sense as a source of wisdom really only tells us about what most people think about the common situations and problems of the day and how most people deal with those. And when we talk about things like nuclear physics or climate change, we're really talking about scales of time and space that are completely outside of what we normally deal with in everyday life, and with causal mechanisms that are totally strange to us. For instance, if the Earth warms by about 5 degrees Fahrenheit by the end of this century, then that's about 80 years. On a daily basis, that means that the Earth the temperature would increase by about 2/10,000ths of a degree accumulated then over those 80 years, and that would equate to that 5 degree increase. So that's a very tiny little measurement. And of course, that's then averaged across the entire Earth's surface over a very long period of time. And so my point is obviously that there's no way we can sense that kind of change. My point is that you and I can't really expect to sense climate change. But we can listen to climate scientists who can tell us about the effect of these tiny changes accumulated over long periods of time and how that might affect, well, the weather patterns we're experiencing today, perhaps increased droughts, periods of excessive rainfall, these sort of weather patterns and how those relate to those tiny accumulations, tiny changes in temperature accumulated over long periods of time.
Is increasing in content. These are observable facts. Again, we can go back in time. We can look at ice bubbles in the ice sheets, and we can map out the concentration of carbon dioxide and see that it's dramatically increasing in the age of fossil fuel burning. I mean, this is not a question. It's just a fact of research. And let's look at a little bit about exactly what's happening and why that would make any difference. Turns out carbon dioxide will absorb energy. So solar radiation, let's look at the basic model. Solar radiation comes in as visible light. Okay, that most solar radiation comes into the Earth's atmosphere as visible light. And you're thinking to yourself, well, boy, we're lucky we have eyes that can see visible light. Otherwise, it would be dark. But of course, all organisms on the Earth with eyes evolved in a world where the available solar radiation was visible light, what we call visible light. We call it visible light because we can see it. So evolution then gives us eyes that we can see the most abundant forms of electromagnetic radiation that are bouncing around down here at the Earth's surface. But in any way, it hits the Earth's surface, is absorbed, it warms the Earth's surface, and then the Earth's surface gives off radiant heat energy or infrared heat. And it turns out that oxygen and nitrogen, which together are 99% of the atmosphere, these two gases, are completely transparent to infrared energy. So if the Earth had an atmosphere that was only oxygen and nitrogen, it would be a very cold place because there wouldn't be any storing of energy in the atmosphere. The energy would hit the Earth, it would be absorbed, it would be re-radiated and go right back out into the solar system or the universe. But it turns out that carbon dioxide and other greenhouse gases, which there are a few, do absorb that energy and increase in temperature. And when that CO2 molecule increases in temperature, it re-radiates the heat in all directions. Some of it heads upward, and if it doesn't hit another greenhouse gas molecule, it goes out into interstellar space. Or it's re-radiated and it goes back down to the Earth and it warms the Earth again, and the Earth heats up and then the Earth re-radiates the heat. So greenhouse gases slow down that movement of heat from the Earth's surface out into beyond the atmosphere, out into the solar system and universe. They slow it down, retain it here in the atmosphere briefly, yes, but importantly, to keep that atmosphere warm in the temperatures in which life can exist. And as we warm the Earth's surface, that Earth's surface then warms the atmosphere. So let's look at greenhouse gases absorb heat energy, right? Whereas oxygen and nitrogen are transparent, okay? Per unit weight, methane is 28 times the ability to absorb infrared energy in comparison to carbon dioxide. So you think we'd be talking about methane all the time and not carbon dioxide, but it turns out carbon dioxide is 217 times more abundant in the atmosphere than methane. So even though it is as much 28 times less potent molecule for molecule, it's 217 times more abundant. So obviously, we're figuring it's accounts for about 75% of greenhouse warming. That methane is also an important greenhouse gas, but the conversation is so much about carbon dioxide. One, because that's the one we're releasing into the atmosphere with the burning of fossil fuels, and it's also the most important of the greenhouse gases in terms of greenhouse warming. The atmosphere is a very big place, 352 million cubic miles or 5.5. I didn't even know there was a quadrillion of anything, but there's 5.5 quadrillion. I didn't need to make that part of my common vocabulary. 5.5 quadrillion metric tons of carbon dioxide or of the atmosphere, if you weighed the atmosphere. Carbon dioxide is a powerful greenhouse gas, yet makes up only about 0.04%. We used to say 0.035, but it's gone up. It's crested 0.04% now. That's only one part in about 2,500. And yet, in our discussion of Earth's climate going back hundreds of millions of years, you can see that releases of greenhouse gases from volcanism yielded a dramatic warming of climate. So even though it's usually a small part of the atmosphere, has dramatic warming effect. It's a combination of the small amount and the large effect that allows human additions of carbon dioxide to be important. If carbon dioxide were 80% of the atmosphere and the temperature was what it is today, we wouldn't have to worry about burning fossil fuels because we would make almost no impact on that 80%. But the fact that it's 0.04%, it has a powerful effect, and yet in small quantities means that when we add small quantities, it starts to change the amount significantly, and then it impacts climate. So it would be, yeah, hard to change it if it were more abundant, but the fact that it's very rare means that we can change it much more easily. Since the beginning of the Industrial Revolution, people have added about 1.5 trillion tons of carbon dioxide to the atmosphere, which if you 1.5 trillion is about 0.03% of 5.5 quadrillion, not the kind of numbers you deal with very often. I love numbers though, so that was fun. So we've released just about as much carbon dioxide as there was in the atmosphere before we released that. And you would think, well, why didn't the atmospheric concentration double? Well, it didn't double because most of that carbon dioxide has gone into solution in the ocean. In a way that mitigates global warming, but it makes worse the problem of ocean acidification. And that itself is certainly really a concept. If you're into, or if you worry about life in the oceans, that's a huge problem. But it does tend to lessen its impact on atmospheric climate change because most of that carbon dioxide has gone into solution. However, as the ocean warms, more and more of that carbon dioxide comes out of solution and back into the atmosphere. Let's look at a little bit of the history of this. This isn't like pop science. This isn't something that, some hippies in the 1970s started thinking about, and in the 1970s in the first Earth Day. This as far back as this is 200 years ago, Joseph Fourier theorizes that the Earth radiated as much heat as it received. If it did that, it would be a very cold place, and so there must be a way of storing that heat. The Earth's atmosphere must be able to hold on to that heat. By the 1850s, a woman named Eunice Foote was the first to discover that gas cylinders full of carbon dioxide absorb more heat energy than other gases, which ends up being a critical part of greenhouse theory and global warming. So that's 50, 100, 170 years ago. By the 1860s, John Tyndall performed further experiments showing that CO2 by itself could absorb multiple wavelengths of infrared energy. Come forward 10 years, come forward another 35 years. I'm sure I can pronounce that very well. Arrhenius, Swedish chemist Arrhenius, was the first to theorize that changes in carbon dioxide contents in the atmosphere could change global temperature. So we're going back into the 19th century. The end of the 19th century, scientists are already speculating on releasing fossil fuel into the atmosphere could change the Earth's climate.
Hey, Tom, we got a question.
Okay.
Which of the Earth's ecosystems, oceans, terrestrial, or freshwater, are more negatively affected by climate change?
Well, climate change, it probably depends whether you're an oceanographer, one who studies life in the Arctic and Antarctic, or whether you're a tropical biologist, which one is worse, because there will be impacts in all of those places. And we're not exactly sure of those impacts. In terms of temperature changes, they will be more important at the poles, which you might say is good for us because we're, mid-latitudes. But it's not good in terms of the melting of polar ice caps and the raising of sea levels and the tremendous impact that's going to have on all terrestrial ecosystems that are along ocean shorelines, much less human infrastructure that's along ocean shorelines. So I don't know if there's an answer to that question. Probably the one that will be impacted most dramatically the soonest will be the Arctic, as we can see permafrost melting today, which then leads to the encroaching of boreal or spruce fir forests are migrating northward onto what was frozen tundra before. So those are some really dramatic changes that are happening in the present, and probably over a matter of coming decades will be the most dramatic one. Beyond that, I'm not sure I could know which one was going to be worse. It's going to be a global level problem. Guy calendar by the early mid 20th century is shows that the temperature of the Earth actually has increased over the last 50 years. So this is, and that was politically controversial until relatively recently. The Guy calendar was claiming to approve that by the late 1930s. And he connected it to increasing carbon dioxide contents in the atmosphere. So again, a theory of climate change that starts to look more modern. In fact, Guy Callender wasn't all that concerned about it because he thought a warming of the Earth would just make the northern latitudes more productive. But he had a relatively modern idea of the relationship between carbon dioxide and the Earth's warming and the fact that the Earth is warming. And but by the middle of the 20th century, 1956, Gilbert Plas formulates what's more or less a modern theory of global warming. And a quote from him, at its present rate of increase, CO2 in the atmosphere will raise the Earth's average temperature 1.5 degrees Fahrenheit every 100 years for centuries to come. If man's industrial growth continues, the Earth's climate will continue to grow warmer. Actually, he's underestimated the amount of warming per century, but it was an important, this is a more or less mature theory of global warming based on a lot of research that's come to fruition in the late 1950s, just a few years after I was born. If you know how old I am, that means we've had this this theory around for a long time. It was an old theory by the days of the first Earth Day in 1970 when I graduated from high school. So let's look at the future of climate change, both global temperature change and what we can do about it. How hot will it get? Well, these graphs have looked pretty similar over the last, since I've been looking at them as a part of my phenology program here and talking about increases in temperature in the future. I mean, the whole reason we have a phenology program at the Conservation District, at least why I'm involved in it, is to understand how our native and well, all plants are responding to changes in weather from year to year to get some hard information about how they might respond to changes in climate or overall increases in temperature. So we can see here a medium increase in temperature is here somewhere around 5 degrees Fahrenheit. I think one of those short videos I talked about that. So that's a sort of average. If we tomorrow you open the newspaper and we've dramatically signed on to pacts and begin to enforce restrictions and reductions on CO2 outputs and all of that, which is pretty unlikely. I think we all know that. Then we might see this lower curve and a total increase of you know, 1.5 degrees Celsius or maybe 2 point something Fahrenheit. Probably not going to happen. And likewise, this highest one where you're talking getting close to 5 degrees Celsius or 8 point something Fahrenheit. Again, I don't think that's realistic. I think people, as the threat becomes real, just as the threat of ozone depletion became very real very quickly, and we responded to it. I think eventually, I know those of you who are pessimists about this may not believe it. I think eventually the human race will come around to it, begin to do dramatic things, and we'll hold it somewhere between a median and a slightly above that. That's, I may seem like a Pollyanna to you, but the day I give up hope is the day I stop teaching. So so let's look at some of these temperature changes. If we think about 5 degree Fahrenheit increase, we can see about what that means in terms of latitude. It's not going as far south as Cairo, Illinois, but it's a little bit south of Springfield, so somewhere in the south central Illinois. That's about 5 degree. If we go as far as south as Cairo, about 8.5 degree, we're pretty near that extreme heat increase. Now, this doesn't, I'm not saying that the climate will be in by the year 2000 or 2100, the climate in Rockford, which is our 0 point here, which is about the same latitude as McHenry County, that the climate here will be the same as the climate in South Central Illinois. I'm just talking about how can we think about it? It could be that the average temperature will be about what it is in South Central Illinois, but patterns of droughts and heavy rainfall will really be quite different from what it is in South Central Illinois today. But moderate levels of climate warming, we're not looking at Louisiana kind of temperatures or the Florida Keys kind of temperatures. We're looking at South Central Illinois temperatures. Now, I'm not trying to belittle climate change. I'm trying to talk about what's most likely to happen and how we should think about the rest of this century and how should we respond to it as conservationists. How do we mitigate climate change? Well, some things are obvious, and that is shifting away from fossil fuels toward renewable energy sources. And I'm not going to talk really much about that. That's really outside of the purview of this talk. I'm not an expert on that, and I really want to save some time to talk about conservation. But renewable energies are happening today. I know they're not happening fast enough, but they are happening today. And it's really quite dramatic how wind farms have swept across the Midwest. They're now supplying a significant part, not the majority, but a significant part of energy for the state. They're not perfect, but they are there at a smaller scale. Solar panels are showing up in lots of places as people want to cut their electric bills. Nuclear power may have a resurgence as small. One of the problems with nuclear power, beyond storing highly toxic fuel for very long periods of time, one of the problems with it has been every single nuclear power plant is done by a different design, and so it takes forever to be approved for use. There are huge cost overruns in their manufacture, and so even if in theory it might seem like a carbon neutral way of producing energy, in practice it's horrendously expensive and politically almost impossible. The promise is of much smaller nuclear reactors that will be built all the same, and so the approval process and may be shorter and easier. And we still haven't solved the problem of long-term storage of highly toxic nuclear waste. But if we're looking at a variety of solutions to what's going to replace fossil fuels, it could be that nuclear energy and those, I don't know what they call them, third or fourth or second generation nuclear reactors might be a part of that. In fact, I would hope that they're not the majority of that, but they might be a part of that. Geoengineering. So that's really about fossil fuels and reducing fossil fuels. Let's look at another way of doing that. We can through geoengineering, we can actually inject aerosols into the upper atmosphere. So we can inject sulfur dioxide into the upper atmosphere to form sulfuric acid and then sulfate particles, and that would screen the Earth. That's highly controversial, both because we're sort of tinkering with the Earth's atmosphere in a direct way without knowing exactly what's going to happen. It is also a short-term method. It's only those sulfur injections in the upper atmosphere would only last a matter of years. We can do carbon capture. This is a method by which we can actually, it's not really filtering, but we could call it filtering carbon dioxide out of the atmosphere, liquefying it. We can either inject it into deep geologic formations to pull carbon dioxide out of the atmosphere. Again, these are controversial because they're seen as a way of avoiding the reality of needing to reduce fossil fuels, but nevertheless, they're on the table now. That is a possible way to do it. It takes a huge amount of energy to do that. So all the energy that we needed to do that would have to be produced by green energy sources. We can inject that liquid carbon dioxide into deep geologic formations where it could be stored, well, for tens of thousands, hundreds of thousands of years. Or we could take that liquid carbon dioxide and use it to make synthetic fuels. So we're now looking at methods of making essentially synthetic gasoline, though they don't call it synthetic gasoline, they call it a synthetic fuel, but it's essentially at a molecular level, essentially identical to gasoline. And you could then use that to burn in a car. So you could then filter the carbon out of the atmosphere, make it into a liquid fuel, put it into your car, burn it, and it goes right back in the, again, this is a short-term cycle, therefore carbon neutral is long. That's a very energy intensive method. And so we have to use huge amounts of green energy in order to capture that carbon dioxide and turn it into a liquid fuel. So that the price of that sort of synthetic fuel is about $40 a gallon now. Not really feasible today for mass use. Might come down in cost somewhat in the future, but that's speculation. Enhanced weathering is a method whereby we take rocks, we pulverize them into a dust. As rocks weather, they actually take up carbon dioxide out of the atmosphere. But rocks weather at a very slow rate, so if we pulverize the rocks down to a dust, we can then greatly increase the rate of weathering and then spread that dust out at the Earth's surface. We can greatly increase the rate of weathering and pull carbon dioxide out of the atmosphere, again, in a very long-term process. So all of these are sort of on the table. There are experiments in enhanced weathering today. They're certainly at an experimental level, or actually a practical level. They've liquefied, filtered carbon dioxide out, liquefied it, and turned it into synthetic fuels. So these are all possible. They're all controversial because they all seem to be an excuse for not reducing our reduction in fossil fuels. But I want to talk more about these last two because those actually have something to do directly with conservation. And that's conserving existing forest stocks and soil stocks of carbon, conserving those rather than plowing up the soils or cutting down the forest. So conserving those, keeping that carbon in a long-term storage, and actually actively sequestering that atmospheric carbon by soil treatments and by growing trees. So that's what we're going to look at next. Carbon sequestration in trees is far enough along that the conservation district is cooperating with the Chicago Regional Trees Initiative to do some carbon sequestration where the conservation district receives some money for growing trees. That's an ongoing thing. We have methods for doing that. Yeah, there are I've forgotten the word for it, but there are bureaucratic methods for quantifying that carbon sequestration and rewarding people for doing it. It turns out a mature tree, this is an average, and what a mature tree is obviously an average concept, but at 48 pounds of carbon dioxide, which is permanently stored in the fibers as a physical event. So every year, 48 pounds of carbon dioxide coming out of the atmosphere. But let's look at how trees grow. This is a growth curve for a tree. I got a forestry degree, so I looked at a lot of these sigmoid growth curves. And what this means is that when a tree is little, if you've grown trees from seed, which I have, you can see that they grow only a matter of an inch or two in that first year, and they start to speed up as they get bigger, and they reach a period of maximum growth. In this particular growth curve that's happening at around, let's see, what's my... so we have slow growth at both ends, rapid growth here in the center. And so the most rapid growth is here right in the middle. The middle part, so there's a period in the growth of this tree where it's sequestering carbon rapidly. It doesn't do much sequestration initially, and once it's achieved its mature form, it's not going to sequester a lot more carbon, and if it dies and rots away, that carbon goes back into the atmosphere. So if we're planting an oak savanna and we expect to have 25 trees per acre at maturity, and in the Midwest, that's reasonable. Our original oak woodlands were not heavily stocked with trees. The carbon sequestration potential is about 325 pounds of carbon per acre per year. Oh, the 48 pounds of carbon dioxide equates to 13 pounds of carbon. So whenever you start to look at the math on this, you have to remember what people are talking about. Pounds of carbon dioxide, there's 2 oxygen molecules there and 1 carbon molecule. So the majority of the weight of carbon dioxide is actually oxygen. So out of that 48 pounds of carbon dioxide, 13 pounds of carbon are sequestered. And so we end up with 325 pounds of carbon per acre per year for that 25 trees. And over 80 years, roughly to the end of the century, we're sequestering about 26,000 pounds or 13 tons per acre of carbon. That's, well, a ton of carbon dioxide is a lot of carbon. That's an acre of ground, roughly, 60, like 200 square, about 200 feet on a side. 13 tons of carbon. That's a lot of carbon dioxide. The problem with that is that it's not nearly enough. If we tried to plant enough trees to suck up all the carbon dioxide we're releasing, there just isn't enough space on the Earth's surface to do that. There was I can't remember the context. There was one of these memes going around about planting 1 trillion trees would, go a long way toward curing the climate change. And the problem with that is if you go through the math, there isn't enough space on the Earth's surface to do that. I mean, you can't plant the Sahara Desert. You can't really plant all the agricultural fields without not growing any food. I mean, it was a nice idea, or maybe not a nice idea, but it was a spectacular idea that is no way on Earth you could ever do it. Literally, in no way on Earth you could ever do it. All right, well, let's look about carbon sequestration in soils. One of the things I remember from my soil classes in college was that this is an acre furrow slice, an acre of about upper 8 inches of soil, which is most of the carbon in soils. There's carbon stored deeper than that, but that's most of the carbon in soils is in that surface, what we call the A horizon or the zone of organic matter accumulation. That's about 2 million pounds per acre. If we can increase that by 5% organic matter increase, and that's a lot. I mean, probably not doable on a lot of farm soils. I mean, actually, the difference between what a corn farm soil is today and what it was as a prairie soil is more than 5%. But actually, increasing it by 5% while doing agriculture is probably optimistic, but we'll just use that as a nice round number. We're going to sequester about 100,000 pounds of organic matter per acre sequestered. About 58% of that is organic matter is carbon. That's 0.58 or 58% is carbon. So about 58,000 pounds of organic or pounds of organic carbon per acre sequestered with that 5% increase, or 29 tons of organic carbon sequestered. And that's really over the next 80 years to the end of the century. My sense is it would probably be a little quicker than 80 years, but we'll just stick with 80 years. So under ideal conditions, both tree planting and soil carbon can achieve, somewhere between 10 and 50 tons. And this is my, high school math, but I just looked online and they're saying 40 to 60 tons of carbon by these biological methods. So we're in the same ballpark over the next 80 years by the end of this century. Nature Conservancy estimates about 148 million acres of land could be reforested. If we did all of that, we could sequester maybe 2 to 5 billion tons of carbon over the next 80 years. And if we could treat all 890 million acres of agricultural land, again, that stretches credulity. We could come up with 15 to 25 billion tons of carbon. I mean, so we're talking about at its far outer limits, tens of billions of tons of carbon sequestered over the rest of this century. And the problem is we're emitting 5 billion tons of carbon every year. And at current rates, that amounts to about 385 billion tons by 2100. I mean, that's both depressing, but it's also carbon sequestration by growing trees and sequestering in soils is significant. It could be between 5 and 10%. That's a big chunk of carbon. So this is important, even though it doesn't solve the problem, it's important. And there are lots of other reasons to plant trees. There are lots of other reasons to rebuild oak savannas, or to replant southern pine forest, or replant Douglas fir forest in the western United States. There are lots of good reasons to plant trees and benefits of that, plus carbon sequestration. Likewise, there are enormous benefits to increasing organic matter contents in soil that allows soil to absorb water much faster. It grows more food faster. I mean, there's all sorts of reasons to increase organic matter contents in soil. So I guess what I'm saying is that this is both important in terms of climate change. It's also not enough. It's a very good thing, but it's not enough. So we get down to conservation in the age of climate change, and this is where we have to reflect back on to my buddy Grog and what he was talking about, because we're now conservationists, looking at the prospects for conserving the beauty and diversity of life going forward. Here we're sitting at 2023, about to become 2024, and we have to think about what can we accomplish. Well, let's first think about what conservation is today and what it was yesterday. And this is my model of conservation today. I'm not talking about conservation, soil conservation and agriculture. I'm not talking about sustainable growth of trees for supply of wood. I'm talking about conservation as we practice it with the conservation district, about conserving the beauty and diversity of life. This is what it is today. I mean, and if you we're protecting remnant natural areas. I don't know how many times we've done our planning in natural resource management and said this is our this is the most important thing we're doing, is protecting remnants. We're restoring areas to native species, and we're protecting the habitats of native species, in particular rare native species. And this is a very tightly overlapping set of goals. And this really describes what conservation is today. And it describes both of these questions about who does conservation and why they do it. Because if you talk to conservationists, talk to someone who has been in conservation for decades of their life, given that much of their life to conservation, and you'll find out why they do it. Even if they don't say, they do it because they fell in love with the natural world. It became a part of who they are, and they can't do anything else. That's why conservation looks this way today. Why we're protecting remnant natural areas, why we're trying to rebuild those natural areas with native species, and why we're protecting the habitats of rare native species. It's because of who's doing it and why they're doing it. And I want to next ask the question, you see implicit in these three circles here: native, protecting remnant or historical remnants. I mean, what does the word native mean? The word native, practically what it means is that things were here prior to European American civilization. It means that plants and animals that were here and ecosystems that were thriving before European American civilization are what we refer to as native today, or remnant. And all of these three key ideas in conservation today revolve around that nativeness. And I want to talk about what that means. I said love for the natural world. I mean, of course, that's why I do what I do. Of course, that's why I'm teaching this course today, along with other courses. That's why I've worked as a manager. It's why I work as a scientist. It's because that natural world just crept into me really as a boy, but it could happen as an adult for some people. It could happen by any number of different avenues. It could be because you went hunting with your father. It could be because you went fishing with your father. It could be because your grandfather loved wildflowers and you followed them around. It could be because your mother was a gardener and you became just entranced with flowers and then wandered into the nearby woods and saw the wildflowers. It could be any number of reasons for that. But as you grow and think about nature and think about your relationship to nature, it deepens. you begin to understand that there are places that hold reservoirs of beauty. And we all learn that as conservationists. I mean, we all learn that we find these places, we may not even understand it in our early years as we become engaged with nature, but we eventually figure out that these are beautiful places because they're still holding on to some character of their past. And then we learn about native plants and exotic plants. We learn about the destruction of invasive species and other forms of habitat destruction. And once you learn that, and once you learn about those places and you learn about native species, and you learn about their disappearance, there's a growing desire to defend and restore these places. Well, of course there is. Whether you can do it physically yourself, whether you can contribute money or time to that. I mean, that's what our volunteer program thrives on, are people that have reached this stage. They want to act to defend and restore the special places, animals, and plants. That grows out of that appreciation as a desire to do something about it. And once you start doing things, you invest in the world. Your life is really sweat equity. You now invested your life in the world, and that increases your love for the world. Those are the reasons. This is the reason why people do it. This is the circle today that defines our love affair with nature, and it's the core reason we do conservation today. And I make this point maybe at too much length, but this is why global climate change is such a disturbing thing, and should be a disturbing thing to conservationists today, because it threatens to make all of these activities untenable, if not impossible. Now, I'll fast forward in a few slides. I don't think it's going to make these things untenable or impossible, but it could. And if you look at some of the literature out there, well, and all you need to do, you don't need to make conservation impossible to fail. All you need to do is make it seem impossible, and people will start to look away. And this is exactly what's happening today in an international level in conservation. These are not cranks or kooks or anti-environmentalists. No, on the contrary, they're ecologists who are deeply involved in conservation today. And they're saying things like, restoring these historic ecosystems, what we would think of as remnants here, is unlikely to be easy or even possible in the changed biophysical conditions of the future. Or many historical restoration targets will be unsustainable in coming decades. Now, I've used these quotes many times. In fact, you can find many others. These just seem to really capture the essence of this group of conservationists and ecologists who are looking into the future and seeing climate change as a dire threat. And we need to pay attention. This is what conservation could look like tomorrow. Not tomorrow, but at some future point. Because we can no longer sustain populations of species where they have historically been present. We have to assist their migration northward. Initially, just the at-risk species, and then maybe other species in time. Meanwhile, we're going to try to maintain ecosystem services, what we might call novel ecosystems, as increasingly the connection between ecosystems and a rapidly warming climate, as that connection with the past becomes less and less and less. They become made up of more and more climate refugees from the south and exotic and invasive species. We might call them novel ecosystems, and we'll be just working to keep some ecosystem services for those novel species while we transport native species northward. I mean, hopefully, if it ever came to that dramatic sort of change, we could fuse these two together, and hopefully those novel systems could be used to house some of those species as we transport them northward. That's about all we could hope for at that point. But the point I would make right now is we're a very long way away from that right now. When I talked about moderate degrees of warming of 5 degrees Fahrenheit, we're talking about our climates in terms of average temperature increasing to something like South Central Illinois. That doesn't preclude holding on to the natural areas we have here today. And I know that's not the end of time. There's a 2200 and a 2300, and we need to think about the future. But in terms of the rest of this century, there is every reason to believe we can hold on to conservation, to what we have today in terms of natural areas and species. Right now, we need to do everything we can to slow climate change, including greenhouse gas reductions, carbon sequestration, and conserving forest, soil, and soil carbon. But right now, this conservation is possible today. And it's possible in the near future. And right now, it's our best chance to conserve the beauty and diversity of life. There's every reason to be concerned about the future, in particular the distant future. But it's also important to realize that we can still make this work today. And the better we can make it work, the more resilient these systems will be to those temperature changes, and the longer we'll be able to hold on to them and hopefully buy time to do something about climate change and prepare for maybe the unfortunate necessity of transporting some of those species northward. Right now, it's our best chance to inspire a new generation of conservationists, just as this inspired the generation of conservationists that are here today. Most of you listening today were inspired by this conservation, and this is the conservation we can use to inspire people today. Losing hope is a way for people to walk away. We need to give them hope. We need to make them concerned about the future. And certainly we need to prepare for that more radical action, but we need to keep people hopeful about the conservation we use today because it is working. And we can make it work for at least for the rest of this century and hopefully into the next century and hopefully well beyond that. So climate change is about the physical reality we find ourselves in today. It's how we understand and how to slow the warming. This is really the science of climate change and applied science of mitigating that change. This is science. It's not speculation. It's not environmental cranks. This is established science. The science on this goes back 200 years, and modern theories of global warming go back to the middle 1950s. I mean, this is established science. We understand it, and we know what we can do to slow the warming. Conservation uses science, but will be guided by our love, our commitments, and our values. I think that's important that we don't start to think of conservation as a board game where we're moving the pieces around. We can still hold on to conservation and to nature as we know it today, and as we knew it in the past. We can still hold on to it today, and we need to do that and hold on to it as tightly as we can and try to help it into the future. And I want to thank you for that. Grog and I both thank you for that. We both enjoyed it, I think. Okay.
Oh, sorry, I was muted. Haha. So thanks, Tom. We're gonna take some time for questions. So we have one in the chat. We'll ask right away, but again, feel free to add your questions in the chat or unmute after we answer this one. What is the total amount of carbon that the Earth's atmosphere can hold?
Well, the Earth's atmosphere could hold huge amounts of carbon. The primitive Earth, before life on Earth, most of the atmosphere was carbon dioxide. So most of those quadrillion tons of atmosphere were carbon dioxide. So in theory, if we could extinguish all life on Earth, that's a pleasant thought. All the carbon would eventually end up in the atmosphere again. It would be the carbon and limestone would be vaporized and sent into the atmosphere. All the life on Earth, all that carbon would go into the atmosphere. So we'd have an atmosphere that was mostly carbon dioxide again. So there's no limit to amount of carbon you can put in the atmosphere. The point is, it makes up a tiny part of the atmosphere now, and even in those very tiny amounts, it has a huge effect on the temperature of the atmosphere. And again, that's science. That's atmospheric science and an understanding of gases and their ability to intercept and store infrared energy that goes back 200 years.
How does removing tiles and ditches in peaty organic soils and resaturating these soils or reestablishing prairies compare to woodland carbon entrapment?
Well, I think there's more potential in soil. The numbers that I showed. I don't know if we can. I'm sure you can read this as I go. I mean, I'm saying that this is maybe, again, they're both exaggerations because we're not going to be able to achieve maximum in either of them. But I think soil carbon storage is more. We can store more carbon in soils than we can in trees, particularly in the Midwest, where our wooded ecosystems were scattered trees and not dense forest. But so number one, draining wetlands is hugely important because that sends all that carbon stored in wetland soils, and depending on the kind of wetland, that can be an awful lot of carbon back in the atmosphere. If you take fens of a highly organic humus-like soil and you dewater them, if you cut off the water supply, all of that soil disappears over a matter of decades. There were fens in England, north of London, where since they drained the fens in the Victorian era with windmills, they've lost, I think it was 18 feet of soil have disappeared, vaporized in that century plus. So that carbon goes back into the atmosphere very rapidly when you dry a soil out. When you plow it up, you expose that organic carbon in the soil to oxygen, and soil rapidly degrades. Our prairie soils were, and I did some studies on soils and remnant prairies some years ago. They're 10% organic matter. If you get into fens, it's over 20%, but even in the uplands in a sort of moist prairie soil, you have percentages of organic matter over 10%. In a farm soil, you're usually well below 5%. So there's a potential there for increases. The more you dry the soil out and till it, the less carbon it can store, all other things being equal. So I think probably soil carbon storage is for us here in the Midwest a more important means for sequestering organic carbon, and I think it will be. I think that it's just starting in conservation now, but that carbon sequestration in soils will start to show up in agriculture here within the next decade. And so yeah, I think that answers the question. I would say probably it's the soil carbon storage that's the more significant. They're both important, but I think it's probably the more important one here in our part of the Midwest.
Anybody else want to ask a question? We're happy to hang out here for a while.
What in my agenda today, I think is pretty obvious. I couldn't tell you anything probably you may not have remembered it, but you probably heard a lot of this stuff about climate change before. It's worth going over, and it's worth recognizing that it's not a new idea, it's an old idea. The model of climate change is now a mature model of it is now over 70 years old, and knowledge of the speculative models are well over a century old now. So this is a established science. I think we all need to think seriously about climate change and conservation. And that's what I tried to capture in the beginning and the end, because it will change how we as a society think about the possibilities of conservation and where people will invest their time and money in conservation. So it is important how we talk about it and what we believe is possible. So yeah, that was the rest of it was a backdrop for that, really, because I think it's a hugely important issue. Climate change isn't going away. It's going to become a bigger and bigger and bigger and bigger topic in conservation as we go forward, and we have to be ready for that and ready to answer those questions that are going to be asked about why are we trying to hold on to these little remnant prairies, if they're not, if you can't hold on to them in the future, and we have to be able to answer that question. Anyway. Well, I want to thank you for coming today. If you don't have any questions, it's good to get back in the saddle again with the Tom Talks. And I hope to see you at our next one. Well, it's going to be in January, I think. That's on that topic will be beaver. That's a really, really neat one. We'll talk about beaver, and it's just an animal, right? But you'll find out it actually is a very, very important animal to all of our stream systems. And you'll probably be surprised to find out just how important it is and was. So if I'll sit here for the next few minutes if you have any questions, but other than that, I guess it's time to say goodbye. Oh, or do we have any more questions? Oh, those are comments I see there.
It's like Joe unmuted. Did you want to ask a question?
Joe always asks good questions, so
Well, if that's the end for today, I just have to remind everybody we'll get the recording of this up within about a day. And you can tell your friends to check it out on our YouTube channel at DiscoverMCCD. We have a Tom Talks playlist. And we'll have another one in January and then a mini series for the first time that we're trying to be a little bit more podcasty and answer questions that you all have shared with us. So we look forward to seeing you soon. And have a wonderful day.